Okay, so now we're going to transition away from reciprocating engines and start looking at turbine engines. So from here on out, we're just going to be talking about turbine engines. Reciprocating engines, fine, I own one. But here at the school, we're supposed to be focused on heavy commercial aviation. Heavy commercial is only turbine engines. There's no magnetos, there's no pressure carburetors, none of that. It's only turbine engines from here on out. And we have a pretty robust staff here that worked on a lot of turbine engine shops. And all of us that basically grew up in the turbine world, we had to kind of learn recip somewhere else. So that'll be helpful to you whenever you get here. But let's talk about the four stages of the engine, and then we'll start to work into how does that factor into the fuel system for a turbine engine. So first off, we have our that's your intake, your induction phase, your suck phase. You're going to suck in that air. Then you're going to have the compression phase. So you've sucked the air in, and you're going to squeeze it together. Now we're going to ignite it. So we've sucked the air in, we've squeezed it, we made like a little bomb right there. Now we're going to ignite it. There, that's our ignition phase. All right, and then we have our power phase. So a lot of times in recip engines, we'll talk about these as being strokes. And I was told that I'm really bad about drawing on the board and getting in front of it. So we'll talk about like the intake. So like you come down, you have your compression stroke as the piston comes up, starts to compress it. The compression stroke will end with ignition. So it's not really a stroke so much as an event. And then you have your power stroke that comes down. So the piston's going up and down, up and down, up and down. And that's a lot of moving parts and pieces that ends up happening to make sure that the engine continues to run. Nothing really wrong or with it, nothing really complicated about it. And all the same things happen with a jet engine. The difference is that whereas these are independent events, the piston comes up, the piston goes down, they're very, very segmented. With a jet engine, it's always happening continuously, all the time. Same couple of steps, but always happening simultaneously. So let's talk about that. All right, so with a recip engine, it's like a little box, and all these things are happening inside of the box. With a jet engine, it's different. I'm going to draw as best I can a rudimentary jet engine. All right, so that's up front. We have it's going to be our fan cowl. This is when you see the big blades turning on the JT9s and stuff. That's what that is. There's a cowling that goes over it, and there's the big turbofan that's in front of it. Now, we'll break down the different types of engines here in future videos that we have turbojets, turbo fans, turboprops, all that good stuff. But for right now, let's just wrap our minds around the JT9 because that's what you're going to be taking apart in class anyways. So you have the fan blade up here spins, and that has all these little, I guess I don't know how you draw it, little fan blades, and that starts to create the intake. So this is our intake stroke right here. Stroke, our intake phase of the engine. Now in the middle here is where compression happens. Now, how does it do this? So is just like you would have a pump, like if you go back and watch the last video, we're talking about moving fuel around. The compression stroke basically takes a combination of vanes and stators move around, the vanes that stay put, and a vane will pass by it, and it has a negative space here which pushes the air forward but into a smaller space, which helps it compress it. And there's multiple iterations of these that go through there. So it comes through here, gets compressed, comes through here, gets compressed, comes through here, gets compressed, and it takes it more. So it goes from like 1 psi to 10 psi to 100 psi to 1,000 psi to 1,000,000 psi. It keeps on going, and it's tighter and tighter and tighter and tighter and tighter all the way out here. So you can see that we're following the same thing with the With the recip engines, you get suck, squeeze. Now next we need the bang. We need an ignition. All right. So here we have. It's going to kind of look like a ball-ish. Depends on the engine. They're generally circular, and this will be our ignition. Now, while this has been happening here with the air, fuel has come up to the engine and it's run alongside the engine, and now we're going to inject fuel into our combustion chamber, all right? And that's all it is. It's just a big, generally ball-ish shape that will have a spray nozzle. Now, it's different than a fuel injector, whereas a fuel injector is right there next to the spark plug, and it's going to, try to help ignition. The spray nozzle literally just sprays fuel in a big pattern. So like you'll do a fuel nozzle check where we run fuel through the engine, and you hold it hold a like a Gatorade bottle or whatever is what we used to use, but anything that would catch that fuel, and you're checking, making sure that the spray nozzle comes out in a uniform pattern and it's not all like wonky or weird or anything, which would indicate that the spray nozzle is somehow damaged or clogged or whatever. You need to fix it. But that fuel sprays into here like this. And then you have this hyper compressed air that's coming in from the compressor scrolls, right? So as it comes in, you have air and fuel that are mixing together, and then you have igniters that sit right there. Now, what's an igniter? An igniter is just basically a really big, like super powerful spark plug, and you can hear it like whenever the igniters kick off, you'll hear it on the ground because that's how strong that electricity is. As it starts to ignite, you get this big explosion, which is like, it's just a big fireball, all right? And then as the fireball starts to expand, it takes that hyper compressed air and then starts pushing out really, really fast. It has to go somewhere. So there's an exhaust nozzle on the back. Now, the exhaust nozzle is going to let the majority of the air just go out the back. That's the afterburners that you see on jets, or whenever you see a jet go by and you see all the air moving out and stuff like that. That's where a lot of that's coming from. However, there's another fan back here that captures that increased speed. Now, as it starts to spin, it spins a shaft that runs through all this, all the way up to the front. And that spinning motion right here spins the compression section and also spins the fan that generates the majority of the thrust that then will translate into lift, all right? So now you can see how this happens all at once. In your start sequence, you'll start to spin the engine up. You'll hear it go, woo, and you remember back from general, you're looking for 11% NG. So NG is just, N is in physics for rotation, and G is representative of the gear, right? So like NP would be like the propeller speed or proper rotor speed, or NR for rotors for helicopters, stuff like that. Anyway, so you're gonna 11% of what the maximum spinning rate is, all right? Once that's going through here, we know we have enough compressed air in the combustion chamber to make this machine work. So we're going to introduce fuel. As we introduce fuel, then we'll introduce a spark. And a lot of times that happens simultaneously depending on the configuration of the aircraft. But that will happen. Boom, boom, boom. And so you can see there's a human element in here that you can hot start an engine. You can get it too much fuel and then it lights off and it has a big flame and does all kinds of damage to the engine and stuff like that. You can also do a hung start where you don't have enough gas in there. All right. So there's always the dude in the cockpit that's making these decisions. And that's going to play into when we start talking about FADEC and hydromechanical here in just a minute. But so that is what is happening. All right. Now, this class is focused on the fuel portion of it. Now, we've talked about the fuel tanks, we've talked about the fuel pumps, and we've talked about the valves and how it gets there and all this good stuff. Let's talk about just this portion of it. So we've got the concept, we have the theory. Now let's talk about some of the unique individual engine components, and then we're going to build that up into the bigger systems. Okay, so behind me here, you have the combustion sections of the JT9. The inside of the combustion section, you're gonna have igniters, which we'll talk about when we get to electrical, and then we also have spray nozzles. So let's look at a couple of different examples of spray nozzles, how they're supposed to work, how they do work, and then what are we gonna do to inspect them and to get familiar with them before we start taking them apart in class. Okay, we're going to start by just looking at a couple of different fuel nozzles to try to get our brain wrapped around what it looks like, and then I'm going to put a graphic up to show you kind of what the idea is. And if I can find a video of a spray test, we'll put that up as well. The nozzle you're looking at right now came out of an Allison 250. Or a Rolls Royce, depending on what era of engine you're looking at. But it's the same engine that goes in the MD500. It goes in the Bell 206s, 407s, so on and so forth. That nozzle right there, you can see like the little ports in it. So like the way you're looking at it from like the spray side, directly at your face, and then away from you is the side where the fuel line actually hooks up to. Now on the combustion chamber of the Allison, and we'll have one of these in class for you to look at. You have a the spray nozzle that goes in the back end of it, and then the fuel line connects directly to that. The fuel flows through the line into the nozzle, and the nozzle sprays it. You can think of this a lot like a shower head. So like you think about the water that comes through your wall, hits the shower head, and it sprays out like that. It's the same concept. The only difference is the shower head, you're just kind of like you adapt it to whatever you like. You can have the little pulsating thing, or maybe the big fan, or a mist, or whatever. This, based on the design of the engine, the design of the combustion chamber, it has to be just so. It has to be exactly right. If it's off a little bit, the engine won't run right. You could damage the engine. It may not run at all. So on and so forth. And so one of the things that you're always going to be looking for is making sure that spray pattern is correct. Now, the way that this particular spray pattern is, you can see there, it's going to create a big circular pattern, and inside it, you're going to have multiple levels of ports that also spray fuel simultaneously. So you can have like this like nice cone of fuel that mixes with the air and then gets ignited. But this is probably one of the more basic ones that you'll see, and that's why I wanted to start it off here, because it's really not that. It fits in the palm of your hand. They're not very big. They're pretty straightforward. And honestly, like if you stay in the GA world or even into the corporate world, for the most part, they're going to be about like that. We start to get into the heavy commercial side, things get a little bit trickier. Okay, on this one you can see how this is off of a CFM 56, which is one of the most common jet engines known to man, because they were the engine that went on the 737 NG series, which there are hundreds of those planes out there. Almost guaranteed, if you've flown, gone to the airport, booked a ticket on American Airlines or something like that, you've flown on a 737 NG. So this is something that you'll likely encounter if you start doing engine maintenance for anybody that operates a 737, which is a lot of people. That you might actually see this exact part that's out there. Now, the way this works is that like the fuel line will go into the left-hand side there. You can kind of see that little boss fitting that tightens up to it, and then this whole fuel nozzle gets put into the combustion chamber. And you notice it bolts onto the combustion chamber, those three flanges right there. But this one is a lot different than the one that we looked last. Last was literally just like the shower head. Now this time you notice that it curves back, it comes forward, and it has a totally different nozzle on the front. There's no ports or anything. It's literally just a cone with a guide post in the middle of it to create the right spray pattern. And here's the thing, is that this isn't going to be the only one on a CFM 56. There's going to be several of them. And so like that is set up so that way it goes in just the right spot, that sprays the fuel in just the right way, so that way it mixes just correctly and then fires off as needed. And so you can kind of start to see the variation. So it depends on the type of engine that you have, as the design of the spray nozzle will follow. They're all unique. They're all different. They all do the exact same thing, but in order to do that thing in that particular engine's context, you're going to have to make sure that it's adapted correctly, designed correctly with the right spray pattern. This one ends up having a big long arm on it, so that way it gets in the right position inside of the can, so that way you can take it on and off, inspect it, and all that good stuff. That's just part of it. So let's look at one more. Okay, so this is one off of a LEAP engine. So you think about the LEAP engine is the new super efficient engine that went on the 737 MAX. So this is the wave of the future. Now, I personally have never really messed with this in particular fuel nozzle, but you can kind of get an idea that you'd end up having two lines that would connect, and then maybe the spray nozzles on the bottom might have it backwards. But the point being is, like, look how unique it is. It's totally different than either one of the other two that we looked at. No, neither one of them had two different fuel. Imports, and then the other one would the one off the CFM56. It was kind of craned up and curved on the inside. This one looks like it just simply just sprays directly out the bottom there on the backside of the combustion chamber. The point being is that, like, every single one of them is different, and every single one of them is there to serve the exact same purpose, to get the right spray pattern, so that way the engine can ignite correctly. Okay, so this is an example of a spray nozzle. Now, spray nozzles have spray patterns, and those patterns will break down into two camps. One is a simplex spray nozzle, which we'll look at in here in a second, and then a duplex spray nozzle, now, or spray pattern. Now, this is a duplex. I could give you a dozen guesses on why it is called that, but you're only going to need one, because there's basically two patterns there. There's a primary spray pattern, and then there's going to be a main spray pattern that follows behind it. Now, the primary spray pattern goes down the center. That's going to be your primary delivery of fuel. The majority of the fuel is going to go to that primary pattern right there. The main pattern is then going to shoot on the outside and create a bubble on it. Now, there's a lot of physics into why that works the most optimum way, but the so what for our scope of knowledge is that it needs to follow that exact pattern. And the maintenance manual, whenever you go to work on one of these, will tell you that. It'll simply say, hey, look, it needs to look just a certain way, look for these particular things. Now, if there's any deviation from that spray pattern, what you're going to end up having to do is clean it. You'll take the spray nozzle out, you'll clean it if the maintenance manual hasn't already told you to. A lot of times they'll tell you to soak it in fuel or some sort of solvent or cleaner or whatever. Some of the spray nozzles, they'll tell you never clean the face of it, because that could also cause damage to happen to the spray nozzle. That as the engine starts to burn, it burns a particular way. It has a certain soot pattern that comes up, and you don't want to change that. So really, this is a world where you have to follow the directions exactly, because these engines are very, very particular, and they're very, very expensive. And so if you make a mistake, it could be and it could be something that is very benign, very simple, but like you could really derail a lot of things happening here. So let's look at a simplex spray pattern, and you can kind of start to see the difference. Okay, so this is a simplex spray nozzle. It's in the name. It's simple. You can see that it's shooting off a fan pattern of highly atomized fuel. Atomization is just a fancy way to say that it's a spray. And so, like, that fuel is, you're trying to decrease the volume of if you look at fuel as a body of fuel, like, so if you had like a tub full of fuel, like, that would be a body. You're trying to decrease the volume, so you're trying to make it smaller while simultaneously increasing the surface area of that body. So that way you're trying to give the smallest group of fuel or part of fuel with the greatest possible surface area, which is going to lead to the greatest interaction with oxygen, which is then going to increase combustion, because you need one part fuel, one part oxygen to make combustion actually happen. So if you can increase the amount of fuel that is available to mate with oxygen to create a flame, you're going to increase efficiency in fuel burn. So that's what this whole atomization process is all about. And the simplex nozzle does it very, very simply. It's just like a spray bottle. There's no crazy dynamics going on inside of the nozzle there to create two different flows and two different bodies of fuel or anything like that. This is really, really just a nozzle that just sprays it out. Pretty simple. Alright, this is the PT6 fuel nozzle. You notice the spray pattern. What you're looking for in this are any dark spots, streaks, or any clouding, indicating that there's more fuel there than we should be. the main thing that this check is looking for is that you want to make sure the fuel burns efficiently, not only just for power, but also to make sure that you don't have any unburnt fuel that's going to pile up in the combustion chamber and then all of a sudden ignite during start or somewhere during the process, or if it's not going to cool, the fuel's not going to cool the combustion chamber as it's supposed to, and you start getting hot spots and you start having problems that way. So the fuel nozzle spray check is probably one of the most important parts you're going to do on like an engine 100 hour. You're going to make sure that the fuel is moving correctly through the spray nozzle. There's no non-conformances in the nozzle itself, in the spray pattern, that then could lead to much bigger problems later on. Changing a nozzle out is not really that big of a deal. Cleaning a nozzle, not really that big of a deal if it's allowed. But the main thing that you want to avoid is having to do maintenance that could have otherwise been prevented through simply checking the spray pattern. All right, so we understand now generally how the fuel is going to interact with the engine once it's there, but how does it get there? And I don't mean like in terms of storage of the fuel, movement of the fuel around the airframe, and then to the engine, but I mean like once it enters into the engine's space, how does it get manipulated and moved around, and how is it controlled? Now, there's two basic components that we're going to see in jet engines. One is a hydromechanical fuel control. That's kind of like, you think about like driving a car, there's stick shifts and automatic. A hydromechanical unit is a stick shift. It gives you a lot more, I guess, inputs on what's happening with the engine. You can blow the engine up, you can keep the engine from running, but it's mechanical, and so like you can turn around and move things in the cockpit that will move things out here to cause the engine to run differently. And so that's the antiquated way that most of these older engines run. Even my helicopter, whenever I first joined the Army, they were on the India model of the OH-58, which had a hydromechanical fuel unit. And so we had to do all kinds of rigging and things like that to make sure that the mechanics of it actually still worked. So let's look at hydromechanical fuel units, and then we'll move on to FADEC, the next one. Okay, so a hydromechanical unit is still in use today. They're still out there. You'll still see them, but by and large, you're starting to see them go away to these either fully FADEC engines or hydromechanical units that have electronic fuel controls. So let's start with just a regular hydromechanical unit, and then we'll talk about one that has an electronic fuel control. Okay, so there's basically two parts to this machine. There is the metering side of it, and then there is the computing side of the machine. All right, so the computing side basically determines how much fuel should the engine be receiving at any one point in time. Now, the computing side is going to look at what's the throttle set at, like all these different inputs that then is going to try to meter out the fuel to meet that demand at the time. Now, once the computing section determines the correct amount of fuel flow, the metering section, through a bunch of cams and servos that you can see in front of you, they deliver the fuel to the actual engine systems. So if you kind of look at the graphic, you'll see that a lot of this is air driven. Then this kind of goes back to using huffer carts to spin up turbines. And it's not just moving the fan blades, but it's also supplying pressurized air to those old mechanical or hydromechanical units to actually operate and work. Then you have a series of pressure fuel lines, and then return and bypass fuel lines, because sometimes the fuel pressure is going to be too great for the engine, and so you need to have a way to reroute that fuel and put it back in the tank, so that way it can be used later on. Just like shoot it overboard or something else like that. Then obviously the pressure fuel line, that makes sense. You're trying to supply engine pressure, so the fuel that flows through this will end up having to go to the combustion section later on. So you need a pressurized line. You can see that there's several different parts and pieces. There's mode solenoids, there's servo metering valve assemblies, fuel bypass valves, mechanical speed governors, vane fuel pumps, so on and so forth. You can can read about this in the 8083 if you want to get really super familiar with it. If you're really interested in engines or engine guys, so you can talk to Hollis or Tyler when you're in class, because this is what they used to do. They used to work on stuff just like this. However, the vast majority of engine maintenance that happens now is going to happen inside of a Part 145 like MRO, back at the manufacturers or something like that. Your job as a regular run-of-the-mill A&P is going to be just pull the engine off, put it into a crate, and send it off to somebody who specializes in this, because this is just one example of a hydromechanical unit. There are dozens and dozens of different variations of this depending on the type of engine, the iteration of that engine, the year of that iteration of that engine, and all that good stuff. That's why effectivity codes are so important, is because when you start getting to these more complex systems, they might have moved the manual mode cam to the other side or something like that, or replaced it all together. And so if you're troubleshooting, you're trying to troubleshoot the wrong engine based on your wiring diagrams, your systems manuals, all that kind of stuff, and it's for the wrong airplane, you're chasing a ghost, and you're never going to get anywhere. And the worst case scenario is that you fix it thinking that you fix it, and then something ends up crashing, or something happens because you messed with something you probably shouldn't have. And so it's best to make sure that the manual and the information that you're using is effective for that plane, for one. Number two is that the majority of this type of work is probably going to be done by a manufacturer or by a service center that's approved by that manufacturer, because they will then have a direct line of communication between the actual engineering team that put this together and who's doing the work to make sure that all the little parts and pieces get put where they're supposed to be. All right, so even though the hydromechanical units are still in use, it's important to note that they are slowly kind of going away. The newer jets, if they don't have FADEC, which is probably going to be kind of more your baseline, especially as time progresses on, the new, at least anything that's been produced in probably the last 20 or 30 years, is going to have a EFCU, and that's the engine fuel control unit that's attached to it. What it does is it helps replace the computing and some functions of the metering that the old hydromechanical unit used to do. The EFCU is basically going to be a computer that then says, like, hey, look, I know that I'm getting X amount of throttle inputs. I know that we're in this mode of flight. I know these things or other things are happening. So therefore, I need to make sure that we have X amount of fuel to go off or to supply to the engine. Now, this is not to be confused with the ECU, which is basically kind of like controls the entirety of the engine. The EFCU, just the fuel control unit, is a down trace element. Now, it may be integrated into the ECU depending on the model of the airplane that we're talking about here, but generally speaking, it's going to kind of be it's a standalone thing off to the side. Now, this isn't too terribly different than like a fuel injected car. If you're going to have an ECU inside of most modern vehicles that does this exact thing. It simply says that, hey, look, I know that this is the throttle input, this is what the ambient air temperature is, this is what the ambient, outside air temperature is, so therefore I know I need to, to put this amount of fuel into the engine because I don't want to be too rich, too lean, or anything else like that. Even the Rotax engines in the RVs that we have on the hangar floor, this is how they meter their fuel. It's fuel injected, and so it's going to sit there. It's going to take in all that relevant data, and then it's going to determine that the engine needs to have X amount of fuel delivered to it. And so that's really kind of all there is to it. If you have something go wrong with one of these, it's like an LRU. It's a little bit more involved in getting one off. There's a bunch of really big cannon plugs that have to come off, and then you'll have to unbolt the whole system. But it comes off as this massive big brick, and it'll go off into a box. It'll go away, and the new one will come on, and you'll have to go through the maintenance manuals to make sure that it is it's integrated correctly into the engine. But that's all it really is doing, is just determine how much fuel is coming into it, and it's replacing some of the old linkages in the hydromechanical unit. So if you come across anything that says like, hey, look, a hydromechanical unit that has electronic fuel control, that's what we're looking at right here. Okay, so now with the digitization of everything, we have another option. It's FADEC. FADEC is an acronym that stands for full authority digital engine control, which means basically the computer runs everything. So the first time you ever crank a 737, you're going to get in there and you're going to notice that like you have to check for the right switchology, a couple things that are set up correctly, but then you're going to reach up and you're going to turn a knob and you're going to say, you know, to start. You're going to see a bunch of indications, and then you're just going to like let it go and put it on run, and it's just going to run, and it's just going to do its own thing. And at that point, your only real input is going to be the throttle back and forth, unless there's an emergency or something crazy happens. But at that point, it's the computer runs everything. That is FADEC. Now, FADEC has gotten so successful and so popular that you're starting to see it even creep into the reset side of the world, where basically you flip a switch and everything just starts on its own, does its own thing. All that good stuff. And so let's talk about what is FADEC, the full authority digital engine control, and how does that impact us as maintainers. Okay, so this is a Allison 250 turboshaft engine. It's a real common engine. We've talked about it in the past. It goes into a lot of your Bell helicopters, your MD 500 series, those types of applications. You're kind of like run-of-the-mill turbine helicopters. The reason why I bring it up is because it's really easy to see a couple of components that you're going to get with a FADEC engine. Now, what is the difference between a hydromechanical unit with an ECU or EFCU and a FADEC engine? Well, in a FADEC engine, there are no mechanical linkages. It's literally electronically controlled valves that open up and close and do all the fuel metering that need to happen electronically without any sort of like throttle linkages or anything else like that. Now, because of that reliance on electricity, there is a component with FADEC that has to be there that otherwise wouldn't be there on normal run-of-the-mill hydromechanical unit engines. Now I've zoomed in on this cylinder. You can see not the cannon plug that's looking at you, but the first cylinder looking device that's right there. Now that is a permanent magnet alternator, a PMA. Basically, it generates electricity if the engine is turning. If the engine continues to turn, it's going to continue to generate electricity, and it's going to generate enough electricity to run the FADEC system. It sits on the opposite side of the starter generator, which is on the right side. That PMA sits there and just continually cranks out electricity to run just the FADEC system, and that's it. And the idea behind it is that if we can give the FADEC system its own electrical control, our own electrical power source, then if we have an engine out or something else like that, then it will turn around and it'll be okay. Like we could lose all of our electric systems, but in theory, the FADEC will still be able to operate because it has its own PMA and its own circuit outside of everything else. Now, FADEC does a lot of really good things. It turns around and makes the engine a lot more powerful because you're going to end up having a lot more efficient fuel burn. You're going to burn less fuel. You're not going to waste anything. And it reduces the pilot workload astronomically. On helicopters back in the day, the pilot used to, whenever they pulled collective, they had to roll throttle on to keep their engine RPMs where they needed to be, because otherwise you would bog the engine down, you'd lose power, and you'd start to fall by increasing the pitch on the collective. And so you'd see all these pilots sitting around with broom handles going up and down like the collective and teaching themselves to roll their wrist one way or the other to try to get in the habit of doing that. Well, now with FADEC, you don't have to do that. You simply just pull a collective up. You set, well, whenever you run it, you start the engine up. Once it gets above 90% NG, the PMA kicks on, and then from then on, it's going to keep on doing its thing no matter what you do to it until you go to shut it down, and there's a shutdown sequence to turn it all off. That means that you can pull the collective up, you can drop the collective down, you can yank and bank, you can put all the load you want to on the rotor, and that FADEC system is going to say, I need to be generating so many RPMs no matter what. And so it's going to add fuel or take away fuel based on whatever is going on to try to optimize that fuel flow to make sure the engine RPM stays exactly where it's supposed to be. It's a pretty awesome system, and once you've flown with FADEC, you'll only ever want to fly with FADEC because it takes so much work off of the pilot themselves. But the main difference for like your test and everything that you're going to want to know is that FADEC is just full authority digital engine control, and there are no mechanical linkages like with the hydromechanical unit that has electronic fuel control attached to it. That's going to be the big difference. Okay, so now that we kind of understand fuel cells, we understand all the components, the the heaters, the valves, the pumps, the lines, all that good stuff. We understand how a engine, uses fuel whenever it is actually in operation. What are the fuel system requirements that we as maintainers need to be aware of? Okay, so if we're going to inspect the entire system, we're going to always be looking for wear, damage, and leaks. Leaks being the big thing. Fuel leaks are not a good thing on an airplane whatsoever because fuel leaks lead to fire, especially when we're talking about big bleed air systems that are at play. Those fuel leaks can easily start a fire locally that then just basically cascades throughout the rest of the plane. So you do not want to have a leak anywhere. The next thing we're looking at into the entire system is making sure that there's no water in the lines whatsoever. Also sediment. You'll have seals that will start to break down. You'll have dirt and grime and all kinds of things that can happen inside the fuel lines. You want to make sure that gets removed, and then the source of it gets plugged or taken care of, however you possibly can. This includes all of our filters and screens. We're looking for any kind of sediment, any sort of slime is another thing that could potentially grow. A lot of these fuel additives will in turn allow for biological growth, and so you're going to want to make sure that the fuel doesn't have some kind of like weird slimy sludge stuff growing that's some sort of microbial life that's taken up residence inside of your fuel system. So if you got any boost pumps that are installed, the system should be checked for leaks by the pumps. Those pumps are known to start leaking. They'll also set up over a period of time and then start to crack. So you don't want to have that at all. You'll run the boost pumps and you'll check the amp meter, make sure that the load meter should read and have all the readings for all the pumps. So that way you can actually see the pumps kicking on. The amp meter showing that, hey, look, there's amperage going out. So that way you know that it's working. When we start talking about fuel tanks, we're going to make sure that all applicable panels in the aircraft skin or structure should be removed so that you can actually look and see the tank itself. And then whenever you're actually inside the fuel tank, if it's a small plane, you're just looking inside of there. If it is a big plane where you can actually get in there and look around, you're looking for general condition of everything. So be it seals, make sure the seals are in good condition. You're going to make sure that there's no FOD. That's a big one inside of fuel tanks. So you don't have any FOD in the tanks. You're going to make sure that all of the pumps, lines, valves, wiring, anything that could potentially be in there, you want to make sure that it is in top-notch condition, because this is not something that's going to get inspected very often. A tank dive on a large aircraft is an event. You can see the guy that you're looking at right now has a gas mask on. That's because of the noxious gases of those fuel fumes that are in there. When you get in there, a lot of times different companies will have different practices, but they'll make you wear booties, and they'll have to be SACA approved. It's this huge ordeal to get inside of a tank. So you don't want to go back in there more than you absolutely have to. And so like making sure that the fuel tank on the inside is 100% correct is absolutely critical. Okay, you're also going to want to check and make sure that the fuel lines are in good working order. You're going to check all your torque stripe. And the big thing with fuel lines is make sure that they don't rub on anything. They are really prone to chafing, and chafing almost always will lead to some sort of breakage in the line. Okay, here's an example of a fuel line that exact thing has happened to. You can see that the elbow right there is starting to wear through because it's rubbed up against something and some sort of damage happened. That's going to lead to, for one, it's going to lead to low fuel pressure, and then number two, you're going to end up having a fuel leak inside of the airplane, and as that fuel leaks inside of the airplane, it could lead to a fire. Now, fuel selector valves are going to make sure that they operate properly. The fuel actually can pass through them, that they don't have any sort of leaking around them. That's going to be the main things. Now, valves are going to be very different. This is off of, I believe, a Cessna 172. From I know it's a Piper Cherokee, and so the Cherokee. Selector valve right there is just going to spin by your hand, but you could end up in a situation where you have electric fuel valves, and you need to make sure that you actuate them. You hear them go. You can check them, by whatever means the maintenance manual requires you to do it, be it with a multimeter or just simply like by visual. All right, same thing with fuel pumps. You're going to go to the maintenance manual. It's going to give you some sort of MOC to run on it to make sure that the fuel pump works correctly. You're going to action them, make sure that it's not only is it working, but is it moving the amount of fuel that it needs to. Okay, the fuel strainers are another thing that you're going to look at. Gaskelators. You're going to make sure that there is no leaks, no dirt, no signs of some sort of nonconformance or something that's not working properly. As a maintainer, there's a certain amount of judgment that you're going to have to develop as you go along to say like, hey, look, this just isn't right. Based on everything that I've seen and done, I know that this just is not working correctly. So you have to develop that sense. You're always going off of what the maintenance manual says, but for the most part, if it doesn't look right, it's probably not right, and it's something you need to take care of. Now, if there is a component that regularly fails in a fuel system, it's the fuel gauges. They are fuel pressure gauges, you name it. They are kind of wonky to begin with, especially on older airplanes. They rely on float switches and that sort of thing, and they are typically less than reliable. So that's why we always take off with full tanks, like if at all possible. But like you're going to end up seeing write-ups that come in there where, hey, look, this fuel gauge is off. There is a certain amount of tolerance that you're going to kind of get with them, where it's like, hey, look, this one's just old and this is just kind of what they do. But at the same time, you want to have a high standard for all your gauges, because that's what's going to tell you what's going on with the engine. And so you're going to make sure that they read correctly. They're not erroneous, both either high or low, and make sure you have just a really good standard for them, even though knowing that they're going to be kind of wonky at times. The newer stuff, the digital stuff, is a lot better. A lot of that struggle is just making sure it's calibrated correctly, so it's reading correctly, and that will get taken care of most on install, but then you might have to do a little bit of work on it on annuals and things like that. But other than that, that is the fuel system in a nutshell that you'll encounter out there in the fleet. So good luck.